Hey everybody, welcome back to the second video in our playlist. This time we're going to talk about running averages, and I've divided this video into two parts so it won't be so long in each one. The first part is going to talk a little bit about the theory and the mathematical derivation of the running average, and then in the part B we'll show some Python implementations. So let's pretend that we've got this scenario. Our boss asks us to estimate the resistance of a particular resistor. Why would we do this? Well, maybe we're building a larger assembly and we have to use a resistor of a certain kind. We've received some information on these resistors from the manufacturer. It's not perfect, and so we might want to have a more accurate estimation of the resistance. But we're starting with the manufacturer's estimate of the true value, which has some uncertainty associated with it. And we have an implicit assumed dynamic model, right? We assume that the resistance is not going to be changing over time. And finally, we've got a voltmeter with which to make measurements of the resistance in ohms. So how should we go about coming up with a better estimate for the resistance? Here's our plan. We're going to take repeated measurements using the voltmeter and then obtain a sequence of measurement values, Z1, Z2, Z3, and so on. And then we're just going to average all the values. That seems like a reasonable plan. So what we would get if we took, say, 50 measurements is a graph that looks something like this. The red dots are the measurements that we've taken. And here I've assumed that the standard deviation of the measurements is half an ohm. The blue line shows the true value, which we don't know, but just for reference, I've put it in there for this. That's what I used in this simulation. I took the true value and I added white noise to it to come up with the measurements. It's essentially the measurement model that we're assuming. So you can see that if we average over time, this ought to come a little bit closer to the truth. So let's review some terminology here. The state that we are trying to estimate is the true resistance value of the resistor. So our state dynamics model is, of course, very simple since it doesn't change over time. The true state at time k is going to be the same as the state was at time k minus 1. We also note that we're dealing with a scalar quantity. There's no vectors or matrices here, and that's done on purpose to keep it simple. So what's the best way to estimate the state of our system? Well, as we mentioned before, we think a pretty reasonable plan is just to average all the measurements. We don't have any other information to tell us that any particular measurement is better than any other, so we should treat them equally and simply average them. And we don't have any reason to believe that our voltmeter is unbiased. Well, let's assume that it's been calibrated pretty recently. Therefore, we ought to just weight them equally, all the measurements, and compute a simple average. We do assume that the average is unbiased because the measurement errors ought to average out to 0. Said another way, the measurement sequence or the sequence of measurement errors ought to be a 0 mean sequence. A simple running average, it will turn out, is very, very similar to a Kalman filter in its mathematical form. In this case, of course, the dynamics are very simple. We don't have to worry about them too much. And a Kalman filter, however, will be able to take into account much more complicated dynamics. So given a sequence of noisy measurements denoted by the Z's, let's compute at each step the best estimate x hat plus at time k of the true value of the state. So at the kth step, the best guess would be the average of all the acquired measurement values. So it's just a normal sum of all the measurements, starting from the oldest, Z1, through the latest we have just received, ZK. Add them all up and divide by k, and that gives us an average. So that's what x hat plus at time k will be. So why is this average the best estimate? Well, as we said before, the dynamics tell us that the quantity is not changing, and therefore the only variability that we should be seeing comes from the measurements themselves, i.e. the measurement noise. So we should try to eliminate that measurement variability by averaging the measurements. And of course, in this example with the constant dynamics, x hat k time k adds the new measurement and averages over all the previous k measurements. Or I should say k minus 1 measurements. Therefore, as much as possible, we want to rid ourselves of the noise by averaging out. We assume the voltmeter is good. It's not biased, right? So it should tend to zero. The noise should tend to zero in the long run. And if we did have a bias, we wouldn't call that noise, of course. We'd have a systematic error, and we'd have to calibrate it out. But noise can't be calibrated out. It must be averaged or filtered out over time. Noise is completely unpredictable. So we have to try to average it out where we can. And that's what a filter is. It's a kind of averaging process. So here's what we'd get if we averaged all 50 measurements. You see in the beginning here, the plus signs, those are the estimates themselves. They're kind of far from the truth, but eventually they start converging towards the true value. Every once in a while they'll go above or below because there's some outliers in the measurements which perturb them in that direction. But all in all, in the long run, it's going to converge to the true value. So once again, here's the sum. We want to convert this to a running average that is recursive, okay? And why do we want to do that? Well, let's suppose that our estimating task is going to go on for a long time, and for some reason we've got a limited computer memory, and we don't want to have to store up all the measurements and add them all up again. We just want to take the last computed average and add a small increment. So to do that, we need to understand what the difference is between x hat plus at time k and x hat plus at time k minus 1, which of course is the same as x hat minus at time k because there's no dynamics. Well, if we look at the sum of the first k minus 1 measurements, that's the same thing as the quantity k minus 1 times x hat k at time k minus 1. So now we can compute the difference between the two, and of course, as we already knew, it's pretty obvious. The difference is just the last measurement. That's the only difference between the estimate at time k minus 1 and the estimate at time k, so we've added a new measurement, zk. But solving for this, for x hat k, we get the following equation. And you'll notice that the last expression on the right is a weighted average of two terms. The old information, which is x hat minus at time k, and the new information, which is nothing but the measurement itself. So we've taken a weighted average. You'll notice by the weights, k minus 1 over k is much larger than 1 over k. In fact, k minus 1 over k approaches 1 as k approaches infinity, and 1 over k approaches 0 as k approaches infinity. Now we can further rearrange the right side and obtain our final recursive formula for the running average. And here we go, step by step. We start with our definition. We split out the first k minus 1 terms, as we mentioned before. Then we replace the sum using that definition, because we now know that the sum of the k minus 1 terms is just k minus 1 times the previous estimate. Then we do a little algebra to distribute the quantities across the k minus 1. Then we rearrange and factor out the factor of 1 over k. Now this formula here on the bottom, this very, very last one, is essentially what the formula for the update of a Kalman filter looks like. You take the old estimate, x hat minus, you take the difference between that and the latest measurement, and that's what's in parentheses, and then you multiply it times the gain, a 1 over k factor. Add those two together, and that's your new updated measurement. So now we've got the recursive algorithm for computing a running average. The procedure is simply just at the kth step to take the current measurement, subtract off from it the old average to obtain the residual, and multiply that residual by a gain factor of 1 over k. Finally, we add this weighted residual to the old average to obtain the new average, and then the whole thing starts over again at the next cycle. Note that we don't have to remember all the previous values or averages, only the last average. We use the latest measurement to correct the last average. And we also need to know what K is, because we have to keep track of K, because we're dividing by, we're taking 1 over K as our gain. But as K goes to infinity, as we said before, 1 over K goes to 0. So eventually our filter, our averaging filter here, is going to ignore all the new measurements. It's going to get confident enough to believe that it knows pretty well that the average is not changing and it's the same as the last, and it won't update. And that's a problem that happens with real-world Kalman filters as well, and we'll talk about that eventually. So here's the formula. X hat K, X hat plus K equals X hat minus K plus 1 over K times the quantity ZK minus X hat minus of K. Okay, so that quantity in brackets, ZK minus X hat K, X hat minus at time K, is called the measurement residual, also called the prefit residual, or the innovation. That's because it's the difference between the measurement and what we expect the measurement to be. Okay, it's the difference between the actual measurement and the predicted measurement. So why is X hat minus time K our predicted measurement? The answer is we've assumed in this case that the state is not changing with time. And so in the absence of any new information, the previous estimate is really the best we've got to go on so far. When we get into a situation where we have non-constant state dynamics, then the predicted measurement will certainly differ from the previous updated estimate. But nonetheless, we expect the predicted measurement to be fairly close to the actual measurement, at least if our dynamic model is any good. And that does it for today. So where are we? We derived the recursive running average algorithm. We've identified the running average equation with the update step in the Kalman filter algorithm. And then in the next video, part B, we're going to take a look at some Python code that implements this running average and also compare it to simple moving averages. We're going to simulate both a constant and a dynamic scalar process to see how well the recursive average filters perform, both the running average and the simple moving average. And that will do it for today. Thank you for watching. We'll see you in the next video.